This conference will now be recorded.
Hello everyone. In this video, we will discuss previous year's questions from IIT-JEE Advanced exam, and that is from the topics thermodynamics. So all the problems will be from thermodynamics chapter. Here we have a paragraph based question, and based on this paragraph there will be question. So we have to understand this paragraph well, and there is a picture also. Here we have a graph where in the y-axis we have St minus H0 joule per mole per Kelvin, and we have temperature in the x-axis. Now here it is mentioned as beta and alpha, and two different lines are there. So this beta and alpha is basically phases, right? Now entropy versus temperature plot for phases alpha and beta, and pressure is fixed at 1 bar is given. So here St and H0, that is actually the entropies of the phases at temperature T, which may be any temperature, and 0 Kelvin. Now the transition temperature for alpha phase to beta phase change is 600 Kelvin. So this is the transition temperature between these two phases. Here Cp beta minus Cp alpha values are given. So these Cp alpha and Cp beta are basically heat capacities of these two phases, alpha and beta respectively. One more information, we can assume that this is independent of temperature, and that is in the range 200 to 700 Kelvin. So whatever will be our calculation, that will be in this range, and we can assume this difference between Cp beta, Cp alpha as independent of temperature. So here the equation that we are going to use is entropy values at two different temperature, and here we are basically we have to find the value of entropy change S beta minus S alpha at 300 Kelvin. Some more extra informations are also there, ln2 value. Now the equation that I will write, that is for S naught alpha phase 600 Kelvin temperature, then again it is for 300. So this is the relation when we have entropy at two different temperatures. Now there will be Cp for alpha ln 600 300. So suppose this is equation number 1. Now the same type of equation we will write for the other phase, which is beta. So everything will be same, only in place of alpha now we will have beta. Cp beta, then as usual just like before, and that is equation number 2. Now equation 2 and equation 1, these two equations, what we will do, we will subtract 1 from 2. Now when we are doing so, we will get in the left hand side S beta 600 minus S alpha 600. And in the right hand side, we will get fine. So we are keeping it within second bracket, and then there will be difference between Cp beta and Cp alpha. Then we have ln value, which will be basically common, and this is basically ln2, right? So ln2 will be common. Now here we need what value? That is this part actually we need. That is asking in the question the value of entropy change S beta minus S alpha at 300. And what about this value in the left hand side? This value is actually 6 minus 5, because 6 that is given for beta and 5 given that is for alpha. Though here it is given in the difference, but we have to remember that S beta minus S alpha at 0, it is actually 0 Kelvin. So this difference we can take it as if it is S beta 0, S beta naught 600 minus S alpha naught 600. So this will be 6 minus 5, and this part basically we are trying to find. And here Cp beta minus Cp alpha, this value is given as 1. So I'm writing here 1 into ln2. Now ln2 is given 0.69. So this part which we are trying to find, that will be equal to 6 minus 5, which is 1, minus ln2. So it will be 1 minus 0.69, right? So it will be around 0.31. So this will be the answer. That is the value of S beta minus S alpha in joule per mole per Kelvin, because this is the unit, we have not changed anything. And in the right hand side it is ln, so it is unitless. So ultimately unit will be same as the unit which we have in the left hand side. This is the final answer, 0.31. We will go to the next question. Now again, as it is a paragraph based question, so same informations are there, but now we have to find enthalpy change, which is H beta minus H alpha, and it is joule per mole. So when it is entropy, the unit is joule per mole per Kelvin, but now it is joule per mole. Again, it is at 300 Kelvin temperature. Now in this case, as it is asking value of enthalpy change, and it is a phase transition, temperature is 600. Remember, this is the phase transition temperature, and this is always at equilibrium. Now as the condition is equilibrium, that is phase change, which is equilibrium condition, and at equilibrium we know that del G not for any reaction, that is always 0. Now if it is 0, then the relationship, that is T del S naught, now this part will be also equal to 0. That means now we can write del H value, which is at 600, that should be equal to T del S. Now T is 600 and del S is 600 and del S is, that is 600. At 600 temperature, it will be basically 1. So in this way, we can get the value of del H naught at 600. So ultimately, we are getting 600. Okay. Now, why this del S value I am writing it as 1? Because in the previous slide, just remember, this is 6 minus alpha. So this difference is basically 6 minus 5. So that is why it will be equal to 1. So directly I have written 600 for temperature, and in the place of del S I have written 1. So it is, we are getting the value of del H naught at 600, which is 600 itself. Next, we need the value of H beta minus H alpha at 300 Kelvin. Now del H naught at 600 minus del H naught at 300. So this is already known. This value actually we need to find out. Now this is equal to del Cp T2 minus T1. Now T2 is here 600 and T1 is 300. And this value we have already just calculated, which is 600. That means here we will put 600. This part we do not know, that we are trying to find. Del Cp we have to consider it as 1. And 600 minus 300, it is, difference is 300. So the value of del H naught at 300, which is nothing but this value, that is H beta minus H alpha, that is actually the value of del H naught. This is actually del H naught at 300, and that is actually we are trying to find. So this should be equal to 600 minus 300. So the answer is 300 joule per mole. So that is the unit, joule per mole. Fine. So this is a paragraph based question. We have solved total 2 parts. The first part is we have found the S beta dot minus S alpha dot, and now we have found the H beta minus H alpha, enthalpy change. Next question is, here also we have a graph which is temperature versus volume. 1 mole of an ideal monoatomic gas undergoes two reversible processes. One is from A to B, this part, and then from B to C, this part. Now this A to B, this is actually adiabatic. So I am writing here adiabatic, A to B. And also notice that when it is moving from B to C, this part, the temperature is fixed at 600. That means this part is isothermal. So A to B adiabatic, B to C isothermal. If the total heat absorbed in the entire process means you are moving from A to B first, then B to C. This is the entire process. The total heat absorbed given RT2 ln 10, and we have to find 2 log V3. Here some informations are also there. Molar heat capacity of the gas at constant pressure, molar heat capacity, that means only for 1 mole. So that is why here we have subscript Cp and M. This is for constant pressure and M is for molar, which is 5/2 R. Now why this value is required, that also we will see. But what we actually have to find, we have to find the net, that is the total heat absorbed. So I am writing it as Q net. Now Q net will be equal to A to B plus B to C. But as the first process is adiabatic, I can write it as 0. So ultimately Q net is equal to QBC. The first process is adiabatic, second one is isothermal. Now Q net value is given, which is R2 ln 2. Sorry, R ln 2. RT2 ln 2. This is already given in the question. RT2 ln 10. And what about QBC? Now QBC, as it is for isothermal, so we will use the formula for calculation of heat, which is at isothermal condition, isothermal reversible condition, and that value is RT2 ln V3 divided by V2. So this is for the second portion where you are changing from V2 T2 to V3 T2. Isothermal condition, so T2 is fixed, but volume is changing from V2 to V3 and it is expansion. So when it is reversible expansion, isothermal condition, this is the formula for Q. That is, in general, I can write it as RT ln V final V initial. So in our case, V final is V3 and V initial is V2. So that is why it is written in this way. Now both side RT2 will be cancelled. So now you are left with ln 10 is equal to ln V3 by V2. But we need the value of 2 log V3. That means if somehow we know the value of V2, then easily we can put the value of V2 in this equation and we can get the value of 2 log V3. ln we can easily change to log. But how to find V2, that is the question. So now keeping this part for some time fixed, what we will move to the another relationship which is applicable for adiabatic condition. We know when it is adiabatic condition, which is for the process A to B. Here this relationship we can write T1 V1 gamma minus 1, T2 V2 gamma minus 1. Now here gamma value is basically Cp divided by Cv. But Cp value is given, you have to find Cv. Now the relationship is Cp minus Cv is equal to R. That means Cv is equal to Cp plus R. Now Cp is 5/2 R plus R. So it will be equal to 7/2 R. Now put here Cp is 5/2 R. 5/2 and this is 2/7 R. It will be reverse. So ultimately we are getting 2 will be cancelled. 1 minute. This 5 by Cp value is 5/2. Sorry, it will be minus, not plus. Cv is Cp minus R. Now Cp is 5/2 R minus R. So it will be 3R/2. So Cp by Cv will be ultimately 5R/2 divided by 3R/2. So it will be 5 divided by 3. So in place of gamma, we will put 5 by 3. So gamma minus 1 is 5 by 3 minus 1, which is 2 by 3. So we will put basically 2 by 3. So T1 temperature is 600, that is already given. V1 is, here it is given. Yes, it is 10 meter cube. So we will put 10 meter cube. Okay, let me keep it as V2, then next I will change it. Just I'm writing it as V1. And in this side, T2, which is given as 60 Kelvin. So I can write here 60. V2 we do not know. This is 2 by 3. This is also 2 by 3 minus 1. Now you can write V2 divided by V1 whole, that is common, and this will be equal to, sorry, gamma minus 1 directly will be 2 by 3. And 600 divided by 60, this is 10. And V2 we do not know, but V1 is 10. So in place of V1 I can write 10. Okay, so what we will be getting ultimately, so here power will be reversed, because this 10, it is in the denominator in the left hand side. Now it will be on the right hand side, and it will be 3 by 2. So 10 to the power 3 by 2 and 10, this is basically 5 by 2. Okay, so V2 that we will be getting as, let me do it clearly so that if there is any confusion. So it is already 10. Now this power, if we bring to the right hand side, we will be left with V2 divided by 10 and 10 to the power 3 by 2. Now V2 is equal to 10 multiplied by 10 to the power 3 by 2, which is equal to 10 to the power 5 by 2. So now we know the value of V2, which is 10 to the power 5 by 2, and we can put it in this first equation, ln 10 equal to ln V3 by V2. But both sides you can ignore ln, and ultimately it will be 10 equal to V3 divided by 10 to the power 5 by 2. So V3 is becoming now 10 multiplied by 10 to the power 5 by 2, and that is equal to 10 to the power 7 by 2. But we need the value of 2 log V3. So 2 log V3, now we will calculate it. 2 log V3 is equal to 2 log 10 to the power 7 by 2. But 7 by 2 you can bring in the out, that is in the left hand side. So it will be 7 by 2 multiplied by 2 log 10. Log 10 is 1. 2 cancel. So ultimately the answer is 7. So in this way we have to think, that is when solving the problem stepwise we have to think. So as it is asking 2 log V3 and total heat absorbed given at 2 ln 10. So we will need to write first this part, and there this part is 0. QBC you can write from the formula of heat, which is applicable for reversible isothermal change. And this side we have written RT2 ln 10, which is already given in the question. Now in this, to solve this problem, you need the value of V2, for which we are using this equation for the first process, which is A to B, because this equation is applicable only for adiabatic. Now gamma you are calculating from Cp by Cv ratios. In this way stepwise we have to solve this problem. In a 1 liter flask, 6 moles of A undergoes this reaction, where from A we are getting the product P. The progress of the product formation at two temperature in Kelvin, T1 and T2, given in the plot. So in the plot, in the y-axis you have concentration of the product P, which is in moles per liter, and time in hour, which is in the x-axis. Two different temperature, you can see the line, and here it is cutting at this point. That means at temperature T1, when it is already reached equilibrium, the corresponding concentration of the product is 4 and same is 2 when it is at temperature T2. Now this equation, to solve this equation, what it is actually asking, T1 is equal to 2T2, that means double of T2, and we have this relation del G2 minus del G1 naught equal to R2 ln x. Now in this equation we have to find what is the value of x. So G1 naught and del G2 naught, they are obviously standard free energy change for two different temperature T1 and T2 respectively. Now as we know the relationship of del G naught, how it is related to equilibrium constant by this relationship RT ln K equilibrium. Now suppose for temperature T1 we will consider the corresponding K equilibrium as 1, and when temperature 2 we will consider the corresponding equilibrium constant as K2. Now from the equation, that is A gaseous in equilibrium with product which is also gaseous. Now first we will do the calculation at T1 Kelvin. So at T1 initial concentration it is 6 moles, it is 0, but suppose x moles are consumed, so 6 minus x, and here it will be also producing x because it is 1:1. So what you are getting for the value of K1, it is the concentration of P divided by the concentration of A, and that is equal to x divided by 6 minus x. But remember at T1 when you have reached equilibrium, the corresponding value of P is 4. That means here x is 4. So if it is 4, then 6 minus 4, 2. So you are getting the value of K1 which is 2. Now the same thing you can also do at other temperature which is T2, but now the K2 value will be, again I am writing, suppose instead of x now I am writing y divided by 6 minus y, but now it is 2. That is the value of concentration of P at equilibrium is 2. So it will be 2 divided by 6 minus 2, that means it is 2 by 4, or you can say it is half. So now we know the values of K2 and K1, and individually we will write the relationship which is del G1, that is equal to RT1 ln K1. Now RT1 is equal to 2T2. So we can write, which is given in the question, and K1 value is ln2. So 2R2 ln 2RT2 ln2, that is the value. And similarly del G2 naught, that will be equal to RT2 ln 1 by half, right? But we need the value of del G2 naught, del G1 naught. So here we will, when we will do this, and that is equal to RT2 ln x. So this relationship is already given in the question. Now in the left hand side you can write, in place of del G2 you can write this one. So I will take RT2 common and I will write ln half, and in place of del G1 you can write this value. So this will be ultimately, it will give you RT2 we have taken common, so it will be 2 ln 2, and here minus, it is plus, so I can write here minus. Now RT2 both side if we cancel, just I am making it, simplifying it, so it will be cancelled both side, and under this condition RT2 ln half, so ln 2, I'm clearing this part so that I can do the equation here. So ln x, which is in the right hand side, that will be equal to ln half and ln 2. Okay, so it will give you 3 ln 2. That means I can write it as ln 2 to the power 3 ln x 2 to the power minus 1. So x is equal to 2 to the power 3 and that will give you 8. So as it is asking the value of x, so x will be equal to 8. Fine. Next question. 2 moles of mercury gas is combusted in a fixed volume Bohm calorimeter. Now Bohm calorimeter, even if it is not mentioned as fixed volume, always remember during this process, volume will remain fixed. We are treating it with excess of oxygen at 298 Kelvin and 1 atmosphere, and it is converted to HGO solid. So here the equation that we can write is Hg gas. So I am writing from for formation of 1 mole of HGO solid. So that is why I have written half oxygen. And we are getting in the right hand side HGOS. Now for this, this is a combustion reaction as it is clear. But what it is actually asking in the question that you have to understand, and accordingly we have to proceed. During the reaction, temperature increases from 298 to 312.8. Heat capacity of the Bohm calorimeter is 20 kilojoule per Kelvin. This is the heat capacity for calorimeter. Enthalpy of formation of Hg gaseous 61.32, which is at 298. That means when you are starting the reaction, we have to find the value of calculated standard molar enthalpy of formation of mercury oxide solid at 298 Kelvin, and that value is x. You have to find the value of x. Now it is within mod, so even if there is negative value, we just have to write the positive value because of this mod sign. Now for this reaction, as I have written here, if I am writing del R, that is for the reaction, the enthalpy change, if I am writing, that will be equal to del HF naught for HGO solid minus del HF naught for Hg gaseous minus del HF naught for oxygen gaseous, half oxygen gaseous. But see, as it is in elemental state, so this value will always be 0. Now so I am directly writing here 0 because it is for oxygen. Now this part is actually unknown, which we have to find. This part we have to find. And this part is given, which is 61.32, and this part is 0. But this is also we do not know. But that you can find from the other informations that is given in the question. Now as it is a constant volume process, so, and if we write the relationship between del H and del U for the Bohm calorimeter reaction, that will be equal to del H equal to del U plus del Ng R into T. Now this del H is actually this value. So somehow if we know the del H value from this Bohm calorimeter, then we can just put it in the previous equation and we can find this unknown value of del H, that is enthalpy of formation of mercury oxide solid. So what we will do here, del U value first of all we need. So separately we will calculate this del U value. Now del U for this combustion reaction, I am writing here com, that is equal to the heat capacity of the Bohm calorimeter, which is 20, multiplied the temperature difference T2 minus T1, which is 312.8 minus 298. Now this will give you the value, but that is for 2 moles. But we need to calculate it for 1 mole. So I will divide it by 2. So ultimately you will see you are getting 20 multiplied by 14.8 divided by 2, and that is equal to 148 kilojoule per mole. Now this is the temperature which is basically absorbed by the calorimeter, because the temperature that will be liberated in this combustion reaction. Combustion reactions are exothermic. So whatever temperature will be released, that will be captured by the Bohm calorimeter. That means this amount of energy which is captured by Bohm calorimeter, when you will put it in this equation, now it will be treated as negative value, because whatever temperature is absorbed, that is actually released temperature. So we will write it here as minus 148. Del Ng is, you just have to subtract the total number of gaseous product, total moles. Now gaseous product we do not have, so this is 0, but in the left hand side we have 1 mole and half. So ultimately it will be 0 minus 1 minus half multiplied by R, which is 8.3. But remember, it is in joule, you have to convert it to kilojoule, that is why divided by 1000 multiplied by 298, because reaction started at 298. So this total value, it will be also negative, minus 148, then minus 3 by 2, 8.3 divided by 10 to the power 3, 298. So after calculation, you will get something negative, which is 151.7 kilojoule per mole. Now you can put this value here, 151.7. Now we know the value of del H. So this part is unknown, and this is 61.32. So ultimately, this part will be equal to minus 151.7, and 61 now it will be to the left hand side. So it will be plus. So this is the value of enthalpy of formation, that is molar enthalpy of formation only for 1 mole for mercury oxide solid at 298, and that is X, but it is negative. We just have to put the mod value, which is nearest integer. If we take, it will be 91 without the negative sign. 1 mole of an ideal gas which is at 900 Kelvin undergoes 2 reversible processes. Number 1, when it is moving from P1 V1 to P2 V2, then second process where it is moving from P2 V2 to P3 V3. Here in the y-axis we have U by R, internal energy divided by universal gas constant, but ultimately the unit is Kelvin unit, because when it is U by R, U unit is joule per mole and R unit is joule per Kelvin per mole. So ultimately the unit will be the unit of Kelvin. And in the x-axis we have entropy. These two values are also given for U by R. If the work done by the gas in the two processes are same, we have to find the value of V3, ln V3 by V2. And these terms we already know. Here molar heat capacity at constant volume CVM for the gas is given 5 by 2 R. Now for the process 1, number 1 process, this is adiabatic. Why it is adiabatic? See, for the process 1, the entropy is fixed at this value. So entropy when constant, it is adiabatic process. And for adiabatic process, the work done, I am writing here W1 because it is for process 1, that is directly equal to del U. And del U is, we have to, as it is moving from this point to this point, the direction is towards downward. So we are moving from 2250 to 450. Now the value of U by R is 2250 when you are at point, suppose it is point A, this is point B. So at point A it is 2250. That means the value of U should be 2250 multiplied by R. So directly I can write that. So this is the final condition, which is point B. Initial condition is point A. So for the final condition, I will write 450R, which is the value of, as if the final U, minus 2250R. So ultimately we are getting 1800R. So this is for the process 1. Now for the second process, here del U will be equal to N CV M del T. Now there is that is temperature difference we have to consider. Now this, that is in the left hand side, we can write And in the right hand side we can write, as it is for 1 mole, 1 multiplied by 5 by 2R, and in place of del T we can write T2 minus T1. Now in this T2 minus T1, that value we can find. And here del U, that is already we have calculated minus 1800, right? So that is why directly I can put the value here. RR will be cancelled, and T2 minus T1, that value we will get minus 720 Kelvin. If it is minus 720 Kelvin, then T1 we already know because we have started the process at 900 Kelvin. So in the right hand side, I can write, that is left hand side T2. Now it is T1 minus 720 Kelvin, but this is 900 Kelvin, which is already given in the question. So T2 now we are getting 10 Kelvin. Now once we know the T2 value, and it is already mentioned that work done by the gas in the two processes are same. So W1 should be equal to W2. Now W1 is minus 1800 R, and W2, that is R T2 ln V3 by V2. So the second process, as you can see, it is in Kelvin unit. That means it is, you can consider as if it is temperature unit, and that is fixed. That means it is isothermal condition. And under this condition, this formula you can use for W2. So both side R will be cancelled, negative sign will be cancelled. T2 value we have already found, which is 180 Kelvin, and we need ln V3 by V2, this value. So it will be 1800 divided by T2, which is nothing but 180. So we are getting the value 10. So here the answer is 10. ln V3 by V2 is 10. So first for the process 1, we have calculated W1 by using this, which this one information we are getting from the plot. Then again del U is also equal to this NCV del T. And here why we are using this equation? Because now we know the del U value, and we need the value of T2. Because if we know T2, then only you can use the third equation where we are getting the final value. So that is why for calculation of T2, we have done this part, and we have found T2, which is 180 Kelvin. Okay. For the reaction X solid, it is converted to Y solid and Z gas. Here we have a plot ln P naught versus 10 to the power 4 T. Now here, this is the x-axis, this is the y-axis, and as you can understand, it is negative. That means this side, if you consider, it is positive, and this part is totally negative. We have negative values of ln Pz P naught. And x-axis 10 to the power 4 and divided by T, that is why the unit is per Kelvin. And y-axis, it is ln Pz by P naught, that is, it is unitless. This information is given. Pz is the, where Pz is the pressure in bar of the gas Z, because only gaseous species is Z. And it is a temperature T, P naught is given 1 bar. Now the equilibrium constant value, dln K d1 by T minus del H naught R. Though this equation is given, but if we integrate it, the process will be a little complex. So without going to that method also we can solve it. Simply by using the formula, we know the relationship between Gibbs free energy and K equilibrium. So here equilibrium constant is given Pz by P naught, and we know the gas constant. We have to find del H naught value. So which equation we are going to use there? We are going to use here del G naught is equal to minus RT ln K equilibrium. And K equilibrium in our case Pz by P naught. But we also know that del G naught is equal to del H naught minus T del S. So what we will do, RT ln Pz P naught, which is nothing but K. that is equal to del H naught minus T del S naught. Now this part we will write in a different way. How we will write? Left hand side we are keeping only this part, and minus RT we will divide here. Minus RT, there is a minus sign. This will be now plus. You will be left with R. Now the next thing is very interesting that you have to do. Why? We are just multiplying 10 to the power 4 and also dividing. So as if we are doing nothing. So why we are doing so? Because if you do so, then only you can get this part, which is basically present in x-axis. Now you can compare this equation with mx plus c. So del S naught by R is c. X is 10 to the power 4 by t, and del H naught by R into 10 to the power 4, that is actually our slope. So here slope, which is m, that is equal to del H naught divided by R into 10 to the power 4. If it is so, now from the graph you can understand this is slope, and when you have to find slope, you have to take this difference and this difference. So first we will do it for y-axis, that is minus 7 minus minus 3, and it is 12 minus 2. Sorry, 12 minus 10, which will give you 2. So ultimately you are getting minus 2. This is the value of slope. Now if you know this, you can also calculate del H naught, and del H naught both sides negative negative cancelled. So you are getting 2 into R multiplied by 10 to the power 4. But del H value, it should be in kilojoule. So R should be divided by 1000. 4. So ultimately it will be 10, and you will get the value as 16628 in kilojoule per mole. So this will be simpler process rather than going to integrate this. That is actually not required. Now the same question, that is it is paragraph based question. So keeping this part fixed, here it is asking value of standard enthalpy. But in the next question, same problem, but now we have to find enthalpy. Not enthalpy. Now we have to find del S naught in kilojoule per Kelvin per mole. Now again we will write the equation, which is ln Pz divided by P naught minus del H naught divided by R into 10 to the power 4. So this is basically our slope multiplied by 10 to the power 4 by t. This is our x, and this is our intercept. Now intercept will give you the value of c. So you can compare this equation as if it is y equal to minus m multiplied by x plus c. So here y is equal to minus 3 if you consider this point, and x is equal to 10, this point, and m is equal to, we already know m is equal to 2, that we have already calculated in the previous slide. Remember, we have calculated m equal to 2. Now if it is so, now we can put all these values in this equation. So we will write here minus 3, then slope we will write minus 2 multiplied by 10, because x is 10. So this is our x, this is our m, and del S naught divided by R. Now you can find del S naught by R, which is minus 3 plus 20, 17 multiplied by R. R you don't have to convert to kilojoule because it is, you have to find it in joule. So it will be ultimately joule per Kelvin, 141.34 joule per Kelvin per mole for this reaction. And this there are some extra information also. We have not used this equation. So without doing that also we can solve this problem. So this is the second answer for the same problem. So we are at the end of the session. Thank you for this.